Now, the last thing that I want to cover in this series of slides is just one different application of polynomials being irreducible. So, it is very interesting and kind of fun to take different polynomials and see if you can be clever enough to apply the right irreducibility test to determine if that's an irreducible polynomial or not, or to see if whether it factors or not. That's not really the only reason that we study these things. And so what I'd like to do is give you another application or another reason to study irreducible polynomials. This application is going to be more at the heart of abstract algebra and not like something that you would necessarily do in a high school math class, just generalized. But what we're going to do is going to require that I pull the wool over your eyes a little bit and present you with a fact that we're not really ready to prove. We will prove this later on in the course. This is something we're going to study, but I'm just going to have to present it a little bit early in order to do this application now. So here is the fact that I just want you to take as fact that we don't quite have enough yet to prove. The fact is that in polynomial rings of the form f adjoined x, when we start with the object f being a field, then all these notions that we've learned the definition of a prime element, an irreducible element, a maximal element. We've learned those definitions in general for an arbitrary ring. And normally they mean different things. However, when you work inside a polynomial ring of the form f adjoined x for f a field, all of these definitions coincide. And so, for instance, working inside of the polynomial ring f adjoined x, an ideal is prime if and only if it's maximal. Things of that nature, which is not true in general, but is true when you work inside of polynomial rings. Again, if we take that as fact, then what we can get is the following theorem. Let's suppose that f is a field. Let's work inside f adjoined x, and let's suppose that p of x is an irreducible polynomial. Because being irreducible is the same as being prime or being maximal, using this fancy fact, then what that means is that the ideal generated by this irreducible polynomial p of x is a maximal ideal inside of f of x, and therefore when we look at the quotient ring f of x modulo the ideal generated by p of x, then what we obtain is a field. As some easy examples of this theorem, let's return to something that we've seen before. Let's work inside the polynomial ring r adjoined x. R is a perfectly good field. And let's look at the polynomial that we know is irreducible, x squared plus 1. A million ways to see that that's irreducible. That's an irreducible polynomial, so by our theorem, the ideal generated by it is maximal. And also by our theorem, then r adjoined x modulo this ideal is a field. We've seen this example before. In fact, we had seen that when we take a look at r adjoined x and we mod out by this particular ideal, in some of our previous slides we've seen that the field we get is actually isomorphic to the complex numbers. Another way of thinking about the complex numbers is kind of like the field r adjoined I. In a similar way, I'm not going to prove it, but the ideas are really similar. The polynomial x squared plus 1, it's irreducible over the real numbers. It's equally irreducible over the rational numbers. And if I can't factor it as real polynomials, I certainly can't factor it as rational polynomials. And so an example we haven't seen before is that we could take the polynomial ring of the rational numbers adjoined x, and we could mod out by the ideal generated by x squared plus 1, where that ideal is sitting within q adjoined x. And we would know by this theorem, because x squared plus 1 is irreducible, that we'd be getting a field. Now it turns out that, so that's the part that's implied by this theorem, what happens is that this field is isomorphic to the field of fractions of the Gaussian integers. That's what I have written, this z parentheses I, open parentheses, so just to review some of our notation from last time. So the field that it happens to be isomorphic to is the field of fractions of the Gaussian integers, or another way of saying that, that is probably a little bit easier to understand, is that the field that you get is isomorphic as a ring to the rational numbers adjoined I, q adjoined I. Here's where we really want to use this theorem. We really want to use this theorem to come up with finite fields with various numbers of elements. I think up until this point, perhaps the only fields we've seen are Z mod P, where P is a prime, and those fields are going to have P elements, so a prime number of elements. What we can now do is we can create finite fields that we hadn't known about before that don't have a prime number of elements, but instead have a prime power number of elements. So what I'd like to work through is an example of a finite field that we can create using this theorem that has 8 elements, or 2 cubed elements. And we can use the ideas that we present in this example to build finite fields of a lot of different sizes. So here's what we should do. Let's take a look at the polynomial f of x, which is x cubed plus x plus 1, and let's be thinking about those coefficients as living in z mod 2 adjoined x. So z mod 2 is a perfectly good field, so we're allowed to do this. Let's let I be the ideal generated by this particular polynomial f of x, just to save me a little breath. Now here we've got a cubic polynomial, so using something that we've seen previously in these slides, it's enough to see that this polynomial is irreducible to just check x is equal to 0 and x is equal to 1 separately and determine that f of those values is not 0. I'm going to try working in modular arithmetic again. 0 cubed plus 0 plus 1 is 1. Mod 2, that's 1. So 0 is not a root of this polynomial. When I plug in 1 for x, I get 1 plus 1 plus 1, which is 3. Mod 2, that's 1. That's also not 0. So by things we've seen earlier in this presentation, this polynomial is irreducible over the field z mod 2. And so according to our theorem, when we take the polynomial ring z mod 2 adjoined x and we mod out by the ideal I, the ideal generated by this polynomial, we get a field. So we know that we have a field. The question is it really true that there are 8 elements there? Now let me convince you that there are 8 elements. Let's, as we did in some of our previous slides, let's use the quotient remainder theorem to take an arbitrary polynomial that lives in this ring z mod 2 adjoined x. Let's take that arbitrary polynomial g of x and let's write it as q of x times f of x plus r of x, where r of x is this remainder. And so what that means is that the remainder is a polynomial in z mod 2 adjoined x that has degree at most 2. Then, according to this decomposition, we've taken an arbitrary polynomial, we've written it as a polynomial multiple of our specific polynomial f of x here, plus a remainder. And so this arbitrary polynomial g of x belongs to the coset r of x plus I, where r of x is that remainder. Because we know that r of x is this remainder, we know that it has degree at most 2. And so what that polynomial looks like is it's something of the form ax squared plus bx plus c. And so every member of this field can be associated with its remainder. It belongs to some sort of coset ax squared plus bx plus c plus I, where the a and the b and the c have to be coefficients in the field z mod 2. So that's what this factor ring really looks like, this z mod 2 z adjoined x modulo I. It looks like things of the forms ax squared plus bx plus c plus I, where a, b, and c are, the only possibilities for a, b, and c are 0 and 1. Now all of these choices actually happen, right? I have 2 choices for a, I have 2 choices for b, I have 2 choices for c. All of these choices are independent and all of them actually occur. So that gives us a total of 2 times 2 times 2, or a total of 8 different cosets of the ideal I inside the polynomial ring z mod 2 z adjoined x. So there are 8 elements in this particular field. Now what I'd like you to do is get familiar with toying around and playing with things and trying to create finite fields with any prime power number of elements. I've put it here specifically as an exercise to construct a field with 49 elements, but I'm hoping at this point in time in the semester that your mind works like this. Okay, what I needed was an irreducible polynomial. I needed to work in z mod pz adjoined x for some prime p. Then I needed an irreducible polynomial, and what I was going to end up with is when I factor out and get a field, I'm going to have the possibilities for the remainder here. Those are going to give me my choices. Okay. The prime p that I've chosen is the number of choices I'm going to have for the coefficients, and the number of copies of p that I have is the number of terms that are involved in the remainder. And so that gives me some hint about what type of polynomial I should be looking for, the degree of it, the degree of a particular irreducible polynomial. So hopefully you can take that, that's my hint as to how to really get started on this, but I hope that you can apply that specifically to come up with a field on your own that has 49 elements, or 7 squared elements. Now let's stop and do a summary of all of the things that we've learned in these slides. After studying these slides and your textbook and working the examples and worksheet that I've provided for you in class, these are the things I'd like you to be able to do. First of all, you need to really know by heart the definition of an irreducible polynomial over a field f. And in knowing that definition, I would like you to understand why it's important to say irreducible over this field, not just irreducible in general, although sometimes I'm sure I find myself saying just irreducible. I'd also like you to know the statements of all of the irreducibility tests we've learned. That's sort of the Eisenstein's criterion. We also learned the mod p irreducibility test. We did also learn some method of polynomials of small degree, just sort of testing for roots. I'd like you to know those statements, what do those tests say, but I'd also like you to know their limitations. So have some examples at hand where Eisenstein will work, mod p won't, mod p will work, Eisenstein won't, and so on and so forth. So know what the limitations of these tests are. And of course I'd like you to be able to apply these tests. If I give you a particular polynomial and it is irreducible, you should be able to prove it somehow. I gave you an example on your worksheet, something where you can't use any of these tests, but it's still easy enough to show that that polynomial is irreducible. So you should be able to come up with some way to show that it's irreducible. You should know how and when you can apply these tests. And last but not least, I'd like you to work with this last application and be able to construct finite fields with various numbers of elements. Nothing too fancy. I probably wouldn't ask you to construct a field with 2 to the 501st elements in it, but what I would ask you to do is primes, various primes, smaller powers, see if you can come up with a finite field with that number of elements.